So today we are ready to move on to the 4 fundamental spaces specified by a matrix. So given a matrix, you already have 4 fundamental spaces. Even though we call them spaces, they are actually subspaces, as you shall see very soon. 4 of them. The first one is the column space. That is something that we have already come across before in some oblique fashion. So let's crystallize it. Let's make it obvious. First of all, let's take a look at what we meant by the column picture and the geometry of Ax equal to b, our system of linear equations. So in the column picture, which lives in the vector space, so to speak, we have a dimension of the output space, that is in Ax equal to b. If you think of x as the input, b is the output, and b lives in Rm. It's got m components because each equation has a constant on the right hand side, and that becomes the component of the vector b. Then what this equation is saying is that if you take the columns of A and start forming linear combinations, at some point you might get B, and that particular linear combination is the solution. So that's what it is saying. So the column picture of linear equations is just that. You're looking for the right linear combination or combinations of the columns of A that gives you B. So to write it explicitly, Ax basically says that is the linear combination of the columns of A, small ai, with the weight xi, and then summing it up, and that's a linear combination. And when that equals B, then the xi's, the small xi's here, that will be the solution. If you put them in a vector, then you get the solution vector, or vectors, because there may be more than one solutions. So that's a column picture, and that is a sophisticated picture that we will be working with. But there was a row picture also that lived in the coordinate space, which means each row was an equation. And this is the kind of stuff that actually forms either lines or curves or surfaces or planes, etc. in the coordinate space. And that is something that we were used to before we started with linear algebra in this course. Now, the solution in this picture would be the point or the set of points that are common in all lines or all shapes defined by each row of the matrix. Each row is an equation. So that's not the view that we have for the rest of the course. And then we had a parallel definition of subspaces. So let's kind of review that. We started with something called the span. A span is all possible linear combinations of a given set of vectors. Let's call those vectors ai, and each one, let's say each one has m elements, so they are members of Rm. That's what I'm saying here. Ai is a member of Rm. Then start forming all possible linear combinations of the n vectors, because our matrix is A, m rows and n columns, so you have n columns, those are n vectors of the kind ai. So start making all possible linear combinations, and that will be a set, an infinite set, because it's all possible linear combinations. And that would look like this. It's a set, that's why you have the curly bracket notations, and a vector z such that z is a linear combination of the columns of ai. So that's that. Now we also know that a subspace is a span of bunch of vectors, in particular the basis vectors. So this span that we have defined right here is a subspace that lives in Rm. We are calling this set here C, and that is going to live in Rm. It could be all of Rm, or could be a part of Rm. It could be a proper subset, or it could be all of it. Now, among the n vectors that you're considering here, those are the columns of A. Suppose only R of them are linearly independent. Then you need only R basis vectors to specify this particular subspace. As you can see, I'm kind of sneaking in all these notations, and being the number of columns, R will turn out to be the rank of the matrix, which is why those are the linearly independent columns. Now, once you have the basis, you also know that the number of basis vectors, which is something that we can call fancifully the cardinality of the basis set, That would be the dimension of this subspace C. All right. Now you know that R can never be more than M because you have only M components. If you take M plus 1 vectors, the extra vector that you have now will necessarily be a linear combination of the other vectors because you cannot have more linearly independent vectors than the number of components in a vector. Nor can it be more than n because you have n columns in the matrix, you have only n vectors to begin with. You can have more than n vectors that are linearly independent when you're starting with only n. So R can never be more than the number of rows or the number of columns, which is something that you know. That is the rank. Rank cannot be more than m or n. So R is less than the minimum, less than or equal to the minimum of m and n. If R happens to be m, the number of rows of the matrix, then C is Rm. It's not a subset, it's all of Rm. So this is all by way of review. We have already done this and you know this. Just to keep this idea fresh in your mind that we're going to define something called the column space. We take the columns of the matrix A being AI, these are column vectors, and then we define a span just like the span that we defined before, identical to it. It's just that instead of Si, we're going to call the coefficients Xi because somehow we want to end up with Ax equal to B in the end. So the column space of A is a set of vectors of the kind Z such that Z is a linear combination of the columns of A. So it's a set of all possible linear combinations of the columns of A, which is just another way of saying the span of the columns of A. It is a subspace and it is a subspace of Rm because each column in A has m components because you have m rows. Now later, much later, I'm going to ask you to compute a subspace. What does that mean? That means you have to give me three things. One is, what is that subspace of? That means the containing space. So you have to write it as though your subspace is a subset of the containing space. And then you have to specify the dimension. In this case, the dimension is the rank of the matrix R. And then you have R vectors that will specify the basis. Those vectors you have to specify as a set of column vectors. So those are the three things I look for. Don't worry, you will start seeing examples very soon. Now let me ask you this question that might be so obvious that it might be kind of insulting your intelligence at this point. How many linearly independent column vectors are there in A? There are R of them, R being the rank of A. What's the dimension of each one of those vectors? That is the number of elements in them. That would be the same as the number of rows in A, so that is M. What's a good basis for the column space of A? That's a bit trickier. Those are the linearly independent columns of A. How do you know what those columns are, linearly independent ones? How do you find them? You go back to our friend Gaussian elimination, and then you take the pivot columns of not the REF, but the original matrix A. That is important because as you perform the row operations to get to REF, you're actually messing with the columns and you're changing the column space. So you have to go back to the original matrix to take the pivot columns. Those are guaranteed to be linearly independent of each other. There are R of them. Those R vectors will form the basis of your column space. I'm hesitating a little bit because there are two things I want to tell you. If you had been performing column operations, then the column space will not change. If you're taking linear combinations of the columns, then after having taken the linear combinations, if you put those linear combinations as a matrix and then compute the column space of that matrix, you will get the same column space as the original matrix because column operations do not change the column space. Do you remember where we actually performed something like that? That is in the Gram-Schmidt process where we messed with columns. We did column operations. So what that is saying is that the column space of the orthogonal version of A given by the Gram-Schmidt process is the same as the column space of A. That is something to keep in mind. The second thing I want to say is that since REF is actually the end product of doing a bunch of row operations, what does not change in that situation would be a space, a span, but the span of the rows of the matrix A, not the columns, but the rows. very soon we will start calling that the row space, obviously. So we are doing REF to find the pivot locations, the columns that contain the pivot, and those columns will form a basis for the column space. Now let's look at what it means. Why are we interested in the column space? In solving AX equal to B, as you know by now, we're looking for that linear combination of the columns of A that will give you B, the constants vector. But then column space contains all possible linear combinations of the columns of A. So if B is a member of that set, if B is a member of that column space, then you know that you have a chance of finding the solution, because you know already that B is a linear combination. It's just a question of finding the right xi's, the right multipliers, so that you can solve the system of linear equations. That's not too difficult. We know how to do that. Conversely, if you know that B is not a member of the column space, you know that you have no chance in hell of finding a solution, because B literally is not a linear combination of the columns of A. Since CA, the column space, is all possible linear combinations, solution is possible if and only if B is a member of the column space. That is a significance. The other thing I just mentioned, the elementary column operations that you performed, for instance, in Gram-Schmidt, will not change the column space. So in going from A to Q using the Gram-Schmidt process, the column space of A is the same as the column space of Q. And what will not change in performing the row operations would be a space called the row space. Now let's take a look at computing the column space. So this is a matrix here. It's a 3 by 3 matrix. Can you see anything special about the elements of this matrix? 1, 2, 3, 5, 7, 11, 13, 17, and those are all prime numbers. So if you do row operations, you cannot really get rid of any one of the rows, because there's no multiple of one row that will actually subtract away from another row to become 0 row. So the rank of this matrix is 3. So the RREF will turn out to be the identity matrix. If you don't believe me, just go ahead and do this. I won't do this in front of you, but let me just tell you what's going to happen. You have 5 here. You want to get rid of 5, so you'll take 5 times the first row, subtract from the second row. You'll get a 0 here, and then some number here. Then you multiply the first row by 13 and subtract from here, you get 0. And then whatever number you have here, multiply that by 17 and divide by that number. Then you get 0 here. Then you get some number here in 2 dots and some other number in 3 dots. Then you can divide the second row by the 2 dots number to make that 1, and the third row by the 3 dots number to make that 1. So you get 1, 1, 1 there. Then you can use that 1, multiply that by 2 and subtract from the first row to get a 0 there, and subtract 3 times the last row from the first row, you get a 0 there. And whatever number you have here, some 4 dots, multiply the last row, the third row, by the 4 dots number and subtract from the second row, you will get 0 there. So eventually you will get the identity matrix. So it's full rank. So what's the column space? If I ask you to compute the column space, what will you do? You will say that column space is equal to R3, it's all of R3, and the basis would be the pivot columns of A, so these 3. That is fine, but it's all of R3, so another perfectly fine basis would be just the identity matrix, I3. Now let's take a tall matrix. This has only 2 columns, the first 2 columns of A, really, of the first example. Now, what's the RREF of A? Again, going through the same procedure, you will see that it's got something like an identity matrix, I2 near the top and a 0 row near the bottom. It is a full column rank matrix. The columns are linearly independent. What's the column space of A? Well, each column's got 3 elements, so it's going to be a subset of R3. The dimension is only 2, and it's a plane of vectors in R3. Now, what's that plane? Can you say that it is defined by this? This would be x-axis and y-axis. Is it the xy plane? It's not. It's a plane defined by these 2 vectors. So you have to go back to the original matrix, and the pivot columns of the original matrix will define the plane. Now, let's take another matrix, this time a wide matrix. So I have one more column there, and as you can see, or as you know for sure, that all 4 columns cannot be linearly independent. Only 2 of them can be because each vector, each column has only 2 elements. There are only 2 rows. So the rank is less than or equal to 2. It turns out that is actually 2 in this case. And if you do the RREF, you will get this. And then you can see that there are pivot columns. Columns 1 and 3 are pivot columns. And what's the column space? Well, the rank is 2. There are 2 pivot columns. So it's going to be a subset of R2. But what kind of subset? It's going to be all of R2 because you already have 2 pivots. So the dimension of the column space is 2. So it's a subspace of dimension 2 within R2, which is all of R2. And the basis, again, by recipe, you're supposed to go to this 1, 5, and 2, 7, but they're linearly independent, 2 of them. That will span all of R2. That means these very nice orthonormal vectors also can be taken as the basis. Any 2 linearly independent vectors in R2 will do. Now, the next example is a rank deficient matrix. That is kind of interesting. So this matrix, I am claiming that it is rank deficient. So the third row is a linear combination of the first 2 rows. Can you figure out the linear combination? Actually, no need to figure out the linear combination that gives you the third row. Just look at the columns. The third column is just the sum of the first 2 columns. So the third column is a linear combination of the first 2 columns. So the rank is 2. And the RREF will turn out to be that. The rank deficiency is 1, which is what we will later call nullity. What's the column space of this matrix? It's a subspace of R3. It's got dimension 2 because there are 2 pivot columns. It's a plane of vectors inside R3. How do you define the plane? Again, not the XY plane that you see in the RREF, but the plane defined by these 2 vectors. So that's very important to keep in mind. Now, another one, here it's even more obvious. The second column is just twice the first column. The rank is 1. RREF is that. It's got only 1 pivot. Rank deficiency is 1. The column space is again going to be a subspace of R3 because each column's got 3 elements. And the dimension is only 1. And it's a line of vectors. And the line is defined by just this vector. Another one, a wide matrix. The second column is twice the first column. The third one is 3 times the first column. And also the second row is 5 times the first row. It has to be that way. If there's only 1 linearly independent column, there will be only 1 linearly independent row also because the row rank is the same as the column. That was the teachable moment there. Alright, so the rank deficiency is again 1. The column space in this case is going to be a subspace of R2 because each column's got 2 elements. And the dimension is 1. It's a line of vectors in R2 and the basis is this. So you have to specify this vector and that will form the basis. Now you might notice that, okay, this vector also is like a scale version of the other vector. So are these 2. So you can actually specify any one of them. But our recipe says that it's the pivot column that we will take. That is the safest way of doing it. These special cases may not happen during your test. Let's continue with our column space of a general matrix, not an example, but a general matrix. Just reiterating once more, reviewing. The column space is a set of all linear combinations of the columns of A. That means the span of the columns of A. If the rank is R, then how many linearly independent columns are there in A? There are R of them. R linearly independent columns forming the basis of the column space. They are the pivot columns. Of the original matrix A, as we saw, you cannot take the pivot columns of the RREF or any other columns unless you have some special case. As you know, the column space is a subspace, so it does contain the 0 vector. All subspaces do. The containing space of the column space is Rm, the so-called output space. In Ax equal to B, the space to which B belongs, that is the output space. Now the significance, once again, is that in Ax equal to B in our system of linear equations, if B is a member of the column space of A, then we have a chance of finding the solution. If B is not, then there is no solution. The equations will turn out to be inconsistent. So column space is a subspace of dimension R in Rm. One more example here, 1116, 2219, 1103. So if you do the REF, you subtract 2 times the first row from the second row, you get 2 minus 2, 0, 2 minus 2, 0 again, 1 minus 2 minus 1, 9 minus 2 times 6, that is 12, that is minus 3, so you get that. Then you subtract the first row from the last row, you get 0 and 0 here, and then you have a minus 1 here at that point. Then you have a minus 3 here. That turns out to be the same as the second row, so you just add the negative of the second row. Third row, you will get zeros there. Then in order to get RREF, you just make sure that the pivot is unity is 1, and then you do the backward substitution to get rid of this element there, and then you get the RREF. So A is a member of the set of matrices of size 3 by 4 or 3 by 4. The column space will live in R3. The rank of A is a number of pivots, that is 2 as you saw here and here. So that would be the number of linearly independent columns. So dimension of column space is 2. And what is the basis? Basis would be the first column and the third column. Not the second column because it doesn't have a pivot. Not the fourth column because it doesn't have a pivot. And not the columns of REF or RREF, but of the original matrix. Very important. So you would specify the column space as column space of A is a subset of R3 of dimension 2. You would write it this way in your exam. And you would write the basis set as a set like that. 1, 2, 1 from here. 1, 1, 0 from here. Now we will move on to the null space in the next video.